Hello everybody, this is Garth. I'm going to be solving a physics problem involving the momentum principle. We're going to be modeling the motion of a soccer ball. We're given a couple things. We're given the initial position of where the ball starts, the velocity from a kick, a time interval of half a second. We know that the ball has a constant downward acceleration due to gravity of negative 9.8 meters per second. And we're asked to find what the velocity of the ball is half a second after it's kicked. We start with the momentum principle, so we have the change in momentum equals F net times change in time. We don't know the mass of the ball though, so we have to divide both sides of the equation by our mass. We're left with the change in velocity equals acceleration times change in time, and we can actually solve for the final velocity. So we can plug in the initial velocity that they give us at the beginning of the problem, our acceleration due to gravity, our time interval, and we can get out the final velocity as a vector in meters per second. In part B, they want to know, assume you want to figure out where the ball is half a second after it's kicked. How would you use, what would you use for the velocity when you're calculating that? Would you use the arithmetic average of the initial and final velocities? Would you use the final velocity of the ball, or would you use the initial velocity? And I say the arithmetic average of the initial and final velocities would be the best, because the initial velocity by itself would be too much, because the ball only decreases its velocity over that time interval due to gravity. The final velocity is too little, because we'd be excluding the interval, the earlier part of the interval with the higher velocity. So yes, the arithmetic average would be the best choice here if you were going to estimate the position of the ball. In part C, they want to figure out the average velocity over that half a second time interval. So we take our final velocity, our initial velocity, we add those, divide by 2, and we get the average velocity as a vector in meters per second. For part D, given that average velocity, they want us to actually find where the ball is half a second later. So we take this average velocity that we just calculated, we take the initial position of the ball that they gave us at the beginning of the problem, we take our half a second time interval, we plug those all in, we get the final position of the ball as a position vector in meters. Now, for part E, they want to know the y component of the ball's velocity at its point. So imagine a parabola that models the ball's momentum. So at the highest point of that parabola, the y component of the velocity is 0, because the tangent line at that top of the parabola, that would be a straight line, so that would be a line of slope 0. So per part F, they give us this equation, they want us to fill it in. So we've got the final y momentum is equal to our initial y momentum plus F net times change in time. So I say that this is the final y momentum. It's mass times the y component of our final velocity, and we have our initial y momentum. That's really the mass times the y component of the initial velocity. So we want to we want to fill that in, and we have the 0 from when the ball reaches its highest point. We have a 16 meters per second upward velocity from when the ball is kicked initially. We have this negative 9.8 meters per second acceleration due to gravity. We have our change in time. So for part D, they actually want us to solve for that change in time, and we get something out, 1.63 seconds. That's how long it takes the ball to get to its highest point in the parabola. So part H says, well, knowing how long it takes to get there, they actually want us to find this maximum height that the ball has. So first we need to find the average velocity in the y direction for this new interval from the point at which the ball is kicked to its highest point. So that's not the half a second interval from earlier. So we want to take the y component of our final velocity, the y component of our initial velocity, add them together, divide by 2, we get the average velocity in the y direction of 8 meters per second. Now we can use the position update formula. So we've got our initial y position, our average y velocity, and our time interval, and we plug that in, and we get the maximum height attained by the ball of 13.04 meters.